Welcome back everyone. In this lecture I will continue to talk about tensor products. So, as we have seen in the last class, the matrix of the tensor product has connections with the Kronecker product of the respective matrices. So, now we will use that to compute what will be the trace of the given tensor product of two linear operators. Okay. So, let me just fix some notations. So, let us take A being actually n by n matrix. So, let us say this is n by n matrix and then B to be P by P matrix. So, now we have seen what is the Kronecker product of A tensor B. So, that is indeed given by, so you take this A11B the blocks A1NB and so on AN1B etcetera ANNB. So, this is the Kronecker product of A and B. So, now where this individual block AIJB is given by, you take the matrix entries of B and then multiply by with AIJ. So, you have AIJ B11 etcetera AIJ B P by 1 etcetera AIJ B this is 1 P and then this is P1 etcetera AIJ B P P. So, this is how the Kronecker product is defined. So, now you can see that what will be the diagonal entries of this A tensor B. So, if you closely look at the A tensor B looks as follows and the diagonal entries are clear what they are. So, this exactly looks as follows. So, you have A11 B11 etcetera A11 B P1. So, this is going to be the let us say the first block and then A11 B P1 etcetera A11 B 1 P. So, likewise you can see that here you have A N1 B11 etcetera A N1 BP1 A N1 B1P A N1 BP and so on. So, what is going to be here? So, this is going to be ANN B11 etcetera ANN BPN BP1 and so on ANN B1P etcetera ANN BPP. So, now what will be the diagonal entries? The diagonal entries are this. So, these entries. So, now you can see that. So, this is going to be in diagonal, this is going to be in diagonal and this is going to be in diagonal, this is going to be diagonal. So, basically we have the diagonal entries A11 B11 plus A11 B22 plus etcetera plus A11 BPP. So, this is coming from this first block, from this block, and similarly each blocks on the diagonals that is going to contribute to the diagonals. So, in particularly the trace of this A tensor B is going to be sum of all these elements. This is exactly given by A N N B11 plus etcetera plus A N N BPP. So, if we use the shorthand notation, you can see that this is exactly equal to AII times BJJ, where I and J runs over. So, which is exactly equal to summation A I times summation B j j, which is exactly trace of A times the trace of B. So, this proves the trace of A tensor B is exactly equal to the trace of A times trace of B. And from this we can immediately conclude that, so whenever we have two linear operators, let us say f from u to u and g from w to w, then this f tensor g will be an operator from u tensor w to u tensor w, and the trace of f tensor g is going to be exactly given by the trace of f times the trace of g. So, this is all some basic linear algebra. So, that actually tells us how to compute the trace. So, indeed what we have done, we have enlarged given two vector spaces V and W to this very big vector spaces V tensor W, and then we could actually understand some of the maps, the tensor products and so on in the trace of the tensor product in terms of the product of the traces. So, this is something like looks very familiar to us. So, this is indeed involved in the product of the characters. Okay. So, if we take the inner product, so recall chi dash, so inner product is given by 1 divided by g summation chi of g chi dash of g bar, where g is in g. So, you can see that the sum is running over the product. So, that product is basically the trace of rho g times trace of rho dash g. So, that is very similar to what we have here. Okay. So, that means the tensor products somewhat easily captures something about this orthogonality. So, I am going to use tensor products to prove orthogonality later. So, once I am done with introducing the tensor products. Okay. So, now we are going to see some more basic properties of the tensor products, which are again very important. So, here is the very important connection between the tensor product and the home space. So, let me write it as a proportion. So, if we take this dual space V star and then tensor with W, okay, again we are doing over tensor over the complex numbers. So, if I do not write this, then it is assumed that everything defined over complex numbers. So, this is naturally isomorphic to the home space V comma W. The home space means all set of all linear maps from V to W. Okay. So, what is V dual? V dual is nothing but home of V comma C. So, home V comma W is nothing but the set of all C linear maps from V to W. So, this is some important vector space isomorphism. So, this is again isomorphism as vector spaces. So, later we will see that this actually holds as G representations. Okay. So, first of all, why do we expect something like this? First, to note that the dimension matches. The dimension of V dual tensor W is nothing but exactly the product of the dimension of V star times dimension of W, but dimension of V star is exactly equal to the dimension of V. So, this is exactly dimension V times dimension W, which is exactly the dimension of the home space. So, this is the dimension of home space V comma W. Okay. So, that means if we establish some injective map or surjective map from these two spaces, that will prove this is indeed isomorphic. But indeed what we are going to do, we are going to actually define a very natural map from between these two spaces. So, let us actually define this from the tensor product to the home space. It is easy, again the other way is also easy, not a problem. So, if we take V dual tensor W. So, then we want to define a map from this tensor to this home space. So, what we do, if we take let us define it on the simple tensors. So, to define, okay, let me go through rigorously. So, if I want to define a map from the tensor product to some other vector space, so we have to use the universal property. So, to define this map, so first we need to define a map from this product V star cross W to this home space. So, again there is a natural map. So, there is this natural iota map. So, what is this map? So, let us define this pi. So, the pi actually defined by, if I take the pair f comma w, then you send it to this map, which is, we call it as f tensor w, which is a map from V to W, which is defined to be f tensor W of u is exactly equal to given by f u of W. And one can check that this map pi is indeed bilinear map. So, check this is indeed bilinear map. Since this is a bilinear map, this is extended to pi bar such that this diagram commutes. So, there exists unique pi bar such that this pi bar the pi is given by iota composition pi bar. So, this is what we have. So, indeed in simplest term, we have this map V star tensor W to this home space home V comma W. So, which is given by, so the simple tensor f tensor W map to the map f tensor W 2, which is map from V to W given by f tensor W of u equal to f of u W. Okay. So, this is the map that we are talking about, and we are going to check this map is indeed isomorphism, and it is easy to check this is a linear map that actually comes from the universal property. So, we can actually define the inverse map explicitly. Maybe let me just define the inverse map. If I start with some f from V to W, which is C linear, then what we can do, we can simply map that to this summation V I star tensor f of V I, where I range from 1 to n. So, what is this V I star? So, let us fix a basis. Here we are making a choice. So, fix a basis V 1 etcetera V n. So, this is the basis of V. So, then we have a natural dual basis of this basis for V star. So, the dual basis we call it as V 1 star etcetera V n star. So, this is the basis of V star. How the dual basis is defined? So, it is defined by the following equation: V I star of V j is given by exactly delta I j. So, this equation defines the dual basis, and they are elements in V star and they form a basis for V star. And using this dual basis, you can actually map this given capital F to this element, and that gives you inverse map for this map. Okay. So, maybe I will leave it to you to check this is indeed inverse map, and so one can also directly check the kernel of pi bar is going to be 0. Maybe I can do that here. So, the kernel of pi bar is indeed 0. Now, let us take some element x in the kernel of pi bar. Note that pi bar is a map from V star tensor W 2 to this home space home V comma W. So, now how this x will look like? So, pi bar of x is 0, but the x will look like sum of simple tensors. So, now we can actually fix a basis here. So, let us fix this the V 1 etcetera V n to be basis of V. So, and then we have this dual basis V 1 star etcetera V n star. So, this is the corresponding dual basis, and this is basis of V star, and let us fix W1 etc. Wm to be basis of W. So, then you can see that this x can be written as linear combination of Aij Vi star tensor Wj, and where I runs power 1 to n and then j runs power 1 to n. So, this is what x can be written, and we know already that these elements will form a basis for this V star tensor W. So, now pi bar of x equal to 0 would imply that. So, pi bar of x 0 would imply that summation Aij and then this Vi star tensor Wj, these maps. So, this is identically 0 on entire capital V. So, this is 0 on entire capital V. So, now what we can do, we can just simply apply it on this basis element Vk and then see what happens. So, x of Vk is going to be exactly summation Aij Vi star tensor Wj of Vk. So, now you know already that the way we defined f tensor W, that tells us that f tensor W on U is f of U times W. So, that means this is going to be exactly summation Aij Vi star applied on Vk times Wj. So, this is what we get, but note that this is nothing but the canonical delta Ijk. So, that means it is equal to 0 or 1 depending upon I equal to k or not. So, then this is going to give us exactly equal to summation, when I equal to k you get Akj, where j runs over and then you get Wj. Now, we know that since pi bar of x is 0, that means this is exactly 0, and that would imply that this is exactly 0. And since Wj form a basis for capital W, that would imply that Akj is 0, and since k is arbitrary, that would imply that Akj is 0 for all k and j. So, that actually proves the linear relation that we had is not going to happen. So, that means x must be 0. So, that implies that kernel of pi bar is 0. So, this proves we have this isomorphism between the tensor product of V dual and W and home of V comma W. So, this is something very important isomorphism, and similar isomorphisms are actually there between the home spaces and so on. Maybe let me give this as exercise. So, here is the exercise and I will leave it to you to check. So, this is if you know little bit of category theory. So, in terms of the natural functors called tensor product and home functor. So, one can actually say that the following isomorphism is nothing but in translated language, the tensor product is left adjoint of home functor. So, this home U tensor V W is as a vector space, again as a vector space isomorphic to home. So, you can move this tensor to the home on the other side, U home V comma W. Okay. So, maybe I will leave this as exercise to prove, and this is again can be proved using some universal properties of tensor product and some natural maps. Maybe I will not get into this. So, now I want to define what is called the tensor algebra, because all this can be. So, whatever objects that I am introducing here, all of them can be made into representations. So, that is why we are interested in this. So, here is the definition of the tensor algebra. So, in this course we are not going to be interested in this tensor algebra structure, but we will be interested in the space itself. The tensor algebra is actually given by direct sum of k-fold tensors. So, what is k-fold tensor? The k-fold tensor, which is denoted by t power k v, is defined to be V tensor etc. tensor V k number of times. in some simple notation we write V power tensor k. So, this is what called k-fold tensor, k-fold tensor product. Now, it is not very difficult to see that if we have some k-fold tensor and then if we have some k dash fold tensor, then we can naturally get k plus k dash fold tensor. So, we can define the following bilinear map from this T k V cross T k dash V to T of k plus k dash V as follows. You take this k fold tensors and then k dash fold tensors and then map them to this k plus k dash fold tensor V 1 etcetera V k tensor V 1 dash etcetera V k dash, and this is going to give us bilinear map, and naturally one can extend this map to the tensor. So, this is a bilinear map, and using the universal property you have the following extension. So, this gives a map from the tensor product of T k V tensor T k dash V to T of k plus k dash V. Again the map is same map, you take V 1 tensor etcetera V k and then tensor with V 1 dash tensor etcetera tensor V k dash, and this is exactly mapped to V 1 tensor etcetera V k tensor V 1 dash etcetera tensor V k dash dash. And you can see that this is like a product that you can define on direct sum of T k V, and that is what called tensor algebra. So, the tensor algebra is as a vector space given by this graded vector space, where the kth graded piece is nothing but k fold tensor product. And from this you can see that from this we have a natural product on T of V which takes k fold tensor times k dash fold tensor to k plus k dash fold tensor. So, you define the product using the above formula. So, then the T k V times T k dash V sits inside T k plus k dash V. So, that is a natural product, and that makes this as graded associative algebra. And if you think about it, so it is not difficult to see T 0 of V is exactly can be identified with complex numbers, and T 1 of V is exactly identified with vector spaces. So, this 1 in this complex number is going to be the unit element in T V. So, this is unit element in T V. So, that means T V actually has unital. So, this is indeed unital graded associative algebra. So, now we can see that if we have any vector space map from V to any unital associative algebra, so that can be naturally extended to T V to A. So, this is the universal property that this tensor algebra has. So, let me write down this universal property. So, I am leaving it to you to check. So, if we have a linear map from V to A, so let us call it T. So, this is a linear map, and this A is given to be unital plus associative algebra. So, then you have this natural map from V to T V, which is given by V map to T 1 V. So, this natural isomorphism we take it to be this iota. So, then we can easily conclude that there exists unique algebra homomorphism T bar such that this diagram commutes. So, this is an algebra C algebra homomorphism such that this diagram actually commutes. So, that actually tells us that this TV is somewhat universally generated associative algebra generated by this capital V. So, maybe I will leave it as exercise that you can prove that TV is generated as a vector space by capital V. And if we fix a basis, so suppose if we fix V1 etc. Vn, maybe let me call it x1 etc. xn. So, this is a basis of capital V. So, then one can prove that TV is indeed the span of x I1 times etc. x Im, where these I1 etc. Im they just comes from 1 to n with m greater than or equal to 0. So, when m is 0, this corresponds to the empty product. So, then it is assumed that x I1 etc. x Im is exactly 1. So, that means TV, so it is indeed basis. So, this is actually one can prove that this is indeed basis of TV. So, TV is generated by this exercise as an associative algebra, and all monomials, non-commutative monomials that you can form from this exercise, they all form a basis. So, basically they are called words. So, these are called words that you can actually form from this exercise. Note that so TV is kind of universal object that is generated by V. So, these exercise, so they will not have any relations among them. So, they are non-commutative variables. So, these exercise or non-commutative variables. Okay. So, what happens if I take only one x? So, then that is easy to see. So, if V is just one dimensional space, then TV is going to be exactly, so maybe let me write capital X as this basis of V. So, then TV is exactly going to be the polynomial algebra generated by x, because if I take any word that is actually coming from x, then it is going to be just powers of x, they all will commute. So, then TV becomes exactly the polynomial algebra generated by this capital X. But it gets interesting even if you take two elements basis. So, suppose V is indeed spanned by Cx and Cy. So, then TV becomes the non-commutative algebra generated by xy. So, non-commutative associative algebra generated by xy. So, in particularly this is going to be span of. So, now we will be able to take any form of this words that actually either it starts with x or starts with y and end with x or ends with y. So, then you will have all possibilities like x, xy power I, and then y xy power j, yeah, maybe I can put y here and y here, sorry, x here. So, some alpha beta gamma delta. So, you can see that this alpha beta they are all coming from 0 to 1 and gamma delta again coming from 0 to 1, and this ij can be anything bigger than 0, and this is going to be our basis for this TV, which is actually generated by these two variables x and y, and they do not have any relations among them. So, if you are interested in the commutative version of this, so that is what called the symmetric algebra. So, the symmetric algebra is simply defined to be the quotient of this TV, where the symmetrization is given by you take the two sided ideal So, you make all the variables to commute, that is all you do. So, you take this two sided ideal generated by the following thing, x tensor y minus y tensor x for all x y comes from capital V. So, then you have made sure that you are indeed getting actually you are making sure that all the variables are actually commuting in this algebra, and this is what called symmetric algebra. And it is not hard to see that the symmetric algebra is also graded. So, you have this natural projection from this T of V to S of V, and if we take the pi of T k of V, so that we can denote it by S k of V, that is the kth graded piece of S of V. So, then it is easy to see that S of V is again direct sum of this S k of V, k range from 0 to infinity. So, now if you think about it, so we can denote this pi of capital Xi to be small xi, denote x1 etc. xn to be basis of capital V. So, then with this notation we can see that this S of V is indeed span of all these monomials formed from xi. Since xi's they commute, you can see that you can take any possible monomial x1 power m1 etc. xn power mn with mi is greater than or equal to 0, and this will form a basis for this S of V. So, if we start with V being G representation, then we will see that all this T V, S V all becomes G representation. So, maybe I will do it in the next class. Thank you.